Now let's take a look at swap partitions and the provisioning of swap altogether, as it is an important component of any operating system. So we've created an ext4 file system which supports nanosecond timestamping of the creation of objects as well as modification of objects. In fact, we didn't mention, but nonetheless, access, modify, and change times are all flagged with nanosecond precision with ext4. However, a very important portion of your operating system's duty surrounds the notion of swapping, so swap provisioning. Now, during installation, you will specify swap in expert mode or have swap configured for you automatically by the distribution's setup. However, as your system matures and more users come online and more applications are put into service, you may find that not enough random access memory is available for those applications or subjects and objects. So swapping allows the operating system to virtualize, so it virtualizes random access memory. And the provisioning of swap allows us to, on the fly, provision additional storage of swap or additional swap storage. This ensures that the performance of the operating system is optimal for the duration of its service to its connected parties. So what does that all mean? Well, first we need to have some way of analyzing the current metrics surrounding swap. So tasks include, for example, 1, analyze current swap configuration. This will tell us whether or not we need additional swap at this particular point. Now, a simple command which we've covered, free, with the M option turned on for human readable, in this case it is an H, by the way, will tell us whether or not the operating system is taking full advantage of swap, which is usually not a good thing. So free M enumerates current memory allocation, including swap. Let's take a look from the shell to see what's happening with this system. So free-M. So what's happening here? Well, the top display, or the first row, includes, of course, headers. The second row includes actual random access memory, which for this system is about 1 gig. And below we see a row which corresponds to the columns, at least these columns, total use and free for swap. The swap configuration for this system is 465 megabytes, of which nothing or none of the megabytes are in use, which is good, and all of the megabytes are free. That's an excellent sign that our system is performing optimally, meaning it's doing the bulk of its tasks in memory. That means this terminal window, which is sudo terminal 0, the gedit window, the GNOME desktop, and everything we do, our input, our output, and so on, is occupying currently 427 megabytes of random access memory, leaving more than half of our random access memory free for other applications. And also note that we are running additional services such as Apache, so this system is not necessarily quite busy, but not necessarily sleeping altogether. Now, oftentimes when these processes are running, by the way, they are indeed sleeping, meaning they're doing nothing. A PS dump will give you a sense for what the process is doing at any particular time. You can do a PSEF or a PSAUX and examine the output, the states of the various processes. Typically, the S indicates that the process is sleeping. So currently, this means we have no need for additional swap, but it's still important to know how to provision that swap in the event that your production systems that are quite busy need the additional swap on the fly. Now again, swap can be provisioned on the fly without having to reboot the system. That's important to note. And free tells us what's happening with the swap. Now to see the absolute swap allocation, another command that's of usage to us or of importance to us is swap on. Swap on with the S option. Swap on, by the way, enables and disables swapping, but also reports on the current swap status. Swap on with S displays current swap, and swap isn't an acronym, but we like to uppercase it just to distinguish it, devices. Now swap devices, we should note as features, include partitions as well as files. So may include partitions and or files. This makes it rather flexible because, for example, supposing on your live system you're not able to identify additional partitions to provision or to dedicate to swap, you can create a file on an existing file system wherever there's space and provision swap that way, thus creating, of course, more I/O on the device, but nonetheless giving you the swap that you need. So, swap on-s, let's take a look to see which devices have been enabled for swapping. So this tells us that device SDA5, or the fifth partition on the first either SCSI or SATA hard drive, is provisioned for swap. And it tells us that it's roughly just about 470 megs or so, 465 megs, in that ballpark, just under 500 megs to round it up. Now, each swap device has an associated priority. The lower the number, the more important the particular device is. As this is the only device that's provisioned, it will be the only device that's used if swap is necessary. Also note that's currently not being used. Another way to identify swap configuration is to grep case insensitively swap from etcfs tab. This should reveal any mount points that are automatically provisioned for persistence when the system is initialized. So here we see a UUID, which corresponds directly to the swap device /dev/SDA5. So this is yet another way to identify your swap configuration. Let's just paste this between the single quotes. So if we grep I from a swap, that is from etcfs tab, we'll see any swap partitions that are defined. So let's just note this enumerates swap devices, and we note devices because swap devices can be partitions and or files that are configured for persistence, meaning they are available across system restarts. So notice the unique UUID associated with the device. Every device has a unique ID. And again, the block ID command, let's just expand on this a bit. So C1, block ID against dev SDA5 will reveal, so reveals unique ID or UUID of, in particular this case, dev SDA5, which is functioning as a swap device. So let's block ID just to make sure that it matches up accordingly. Dev SDA5, and as we can see, the UUID of 1F terminating with 89A7 is the unique identifier of dev SDA5. So indeed, it's referenced via its unique identifier, which begs the question, what if we provision a swap file within an existing, let's say, ext4 file system? How does the UUID come into play? Well, you can base it, for example, based on the fact that the ext4 file system in and of itself has a unique ID, which is referenceable, followed by the location in the file system of the given swap file. So that is the device that's in play. Swap on-s reveals that device. Now, how do we provision additional swap storage? Well, let's just take this to another task, which will be to provision additional swap partition initially, then file, which is what we like to do. Well, first, as a note, it makes sense. So before we do it, let's just note it's advised to provision swap on non-user FSs, or file systems that are currently not in usage for general user communications and I/O. And that is because of contention. Now, in today's fast-paced bus environments, whether it's connectivity on macOS, platforms like Thunderbolt or Firewire or USB 3 or otherwise, perhaps contention is less of an issue because devices move faster. But then as your user community and application community grows, that number dwindles, the bandwidth dwindles. So there's always contention at some point, at some margin. So it's always advised, if possible, to segregate swap from user space storage of files. So place swap one place and place user storage another place. And this is across operating systems. It's just a matter of reducing contention and allowing the maximum bandwidth to be realized. So which is why, for example, we're always advised to separate user storage, let's say on RAID devices, and swap on separate RAID devices across operating systems, Windows, Linux, Solaris, etc. So what does that mean altogether? Well, it means we need to first identify what's available for us to provision this additional swap partition on. So let's reset this buffer and fdisk L, the current hard drive layout. So DevSDB1 is currently associated, if you recall, with /var2, which we've yet to populate with data from /var. Perhaps we'll make that the rsync section. Now, DevSDB contains space where we could provision swap, but assuming that eventually the system will begin to use DevSDB, the device, for its var activities, perhaps we should consider DevSDD or DevSDC as an alternate destination for swap activity. In other words, separate I/O channels. Because remember, the processor and memory on most PCs, most systems, outclass all of the other storage I/O. So the more disks and the more memory you can feed into the processor, the more disks, the more disks or storage you can feed into the processor and memory, the more you spread out the bandwidth capability of the processor and memory. So the fastest components on all of your computers will be processor and memory. The slower components tend to be storage of all types, optical, USB, FireWire, SD, so on and so forth, even Thunderbolt. So with that said, let's pick SDC as the target. So identify distinct storage device for swap. Again, there's nothing to prevent us from placing the swap storage on an existing disk such as DevSDB. It's just advisable for I/O purposes, for maximum bandwidth efficiency, that we place the swap elsewhere. So that means we need to create a new partition. So the next step for us will be to use fdisk yet again against DevSDC. So we've identified DevSDC. And once connected, we'll examine the partition table and then create a new partition. So let's go ahead and fdisk DevSDB or DevSDC, print the table, it's blank, new partition, primary, it's the first partition, partition number 1, so this will become DevSDC1, and it'll begin at the first cylinder, and we'll determine how big to make it. Now, a general rule of thumb with respect to swap allocation is to double random access memory. Now, if we recall, free with the M option tells us that we have a gig of memory. So that means we should consider making our swap 2 gigs or 2048 megabytes. We could just indicate 2G, for example, and then print the table. So now 2 gigs of the 10 gigs will be provisioned for swap. But we're not done here. By default, when you use fdisk, partitions that are created are of type 83 or type Linux. This is not the proper type for swap. The swap type is a different type. So let's just note, we printed the partition table, we created a new item, we labeled it number 1, the fact that it's primary, and once it's created, indexing it at 1 and terminating at 2 gigabytes, we then need to flag it. So the next step is to flag the partition, and that's the partition DevSDC1, which is now created as type swap. Now Linux supports many types of file systems. T will allow us to enumerate those file system types. So let's just indicate that. So to flag this, what we do is indicate T followed by L to list the various types. Here are all of the types that this kernel supports, and we need to pick the type for Linux swap. Now, as mentioned, 83 is Linux, 82 is Linux swap, and there are other types, 8E for example for LVM. So we need to set the type of this partition, and it's going to be type 82, which is Linux swap. Once we've set it, we'll P to print to ensure that the changes have been applied to the partition. So now it's of type 82. If you don't take this step using fdisk or parted or some other tool, you'll not be able to enable swapping on the partition or at the partition level. You'll be able to create an ext4 file system and then create a swap file if you'd like, but not a swap partition out of the entire partition. So we've listed and then we've assigned type 82, which is for Linux swapping purposes. It's also shared by Solaris. With that said, we also need to save the changes, so let's go ahead and write the changes to the partition table. And if all goes well, we'll be able to create the swap partition. So far so good. So we're 2 for 2. So now we have a new partition. Now let's confirm from user space, from the shell, outside of the auspices of fdisk, that the partition is indeed intact, using fdisk-l to list Deb6x. So Deb6x contains Deb6x1 or SDC1, which is of type 82. If you're wondering, could we enumerate SDC1 specifically? Well, SDC1 is not a disk, it's a partition. fdisk accepts as an argument disks, and within the context of a disk are one or more, or is one or more partitions. So we now have this new partition. So how do we enable swapping? What's the next step in the process to turn this thing into a swap or a swappable, an accessible device? So we've confirmed everything. We know that it's available. The next step for us is to enable swapping. So we have to actually specify that swapping is to happen on this particular partition. Now, just like we've executed makefs ext4, if you recall when creating the ext4 file system recently, there's a similar command for enabling swapping. So let's go ahead and list that. So the next step for us, we executed fdisk-l Deb6x, confirm that swap partition is viewable by the kernel. And let's just note, by the way, if the kernel encounters difficulty enumerating the swap partition, reboot. So, next step for us. Just like there's a makefs ext4 or make2fs, and with the appropriate options, you can enable the type of file system 2, 3, or 4 of ext that you'd like. There is a make swap. So make swap makes a swap partition out of a particular partition, insofar as the kernel is concerned. So we'll make swap on Deb6x1. This is the step in user space which creates the swap file system on Deb6x1. So whenever you're partitioning a disk, you first need to use a tool like fdisk or parted from the disk level to segment the disk. That's partitioning. You then need, from an operating system level, to overlay a file system, whether it's swap, ext3, 2 or 4, riser, UFS, XFS, NTFS, FAT, you name it. You need to overlay a file system. We're always overlaying file systems unless we're using an application, again, like Oracle DB, which can take advantage of raw partitions. So we're going to make swap on Deb6x1. This will overlay the appropriate file system on the device SDC1. And just like that, we've set up swap space. Also note that there's a unique ID associated with this particular swap storage. It doesn't have a label, but if you have a UUID, a label is unnecessary. Also note that it's about 2 gigabytes. So let's just note, as our next step, we want to set up Deb6x1 in etcfs tab for persistence using the UUID. Since we have it, we've extracted the UUID. And by the way, if you've cleared screen, for example, and have omitted to extract the UUID, it's always available if you use block ID. So block ID against the newly created dev tree node of Deb6x1 will reveal the same UUID. But this format is sans quotes, which is suitable for entry into etcfs tab. So let's nano etcfs tab. And this will allow us to create the item. So we'll create it in this section here. And we'll just use the same thing. This is for floppy, which is a non-issue here. We don't need this. We'll just comment that out. And let's include our comment, LCBT classroom swap mount for Deb6x1. Really, it's for the UUID. We should get away from this notion of tying our mounts to dev tree entries as opposed to the more reliable UUID. But it's going to take a while because for those of us, myself included, we're so accustomed to simply referencing the dev tree location. But the dev tree location is subject to UDEV, which means it's likely to change. Not often, but it's likely to. As you shuffle things around your system, it is likely to change. The same happens on other OSs like Windows, by the way. But if you're operating stable services, production systems that don't change often, then this is less of an issue. So this will be a swap partition. So it doesn't have a mount point, by the way. It's just none, and it's of type swap. And it isn't checked. So the option's just swap, and it isn't checked. So it's just 0, 0. This is the default for a swap file system. So it isn't mounted at a particular mount point. Again, you can create swap storage on an existing ext4 file system, or 3 or 2 if you'd like, or any type of file system. But swap partitions are not mounted in a particular location. In fact, let's just take this entry and paste into our notes to indicate that this is what we entered into etcfs tab for persistence. So let's just note in between single quotes that this is the entry. So that's the entry. And of course, we'll save the changes. And of course, if we swap on, this will enable swapping based on etcfs tab. So now that we have the entry in etcfs tab, the next step for us is to enable swapping via swap on. The command swap on will provision the item on the fly. So this is the user space step where we make the swap storage available. This is akin to mounting the ext4 file system at a mount point, making it available for users who are connected to the system. So swap on, and instead of the S option, which displays the current swap devices, swap on with the A option enables swapping. So this enables swapping on all etcfs tab listed devices. So it's a wholesale way of doing it. Now you could specify the device individually or distinctly from the command line. That's an option as well. But because we're sure that this block ID is solid, that it will mount, we'll just go ahead and forego the step of testing it out initially. But you could test it out initially by swapping on the specific device. So let's swap on -A. Now let's echo the exit status and swap on -S. And there's the additional swap storage. Now, again, if you execute swap on with the help option, you'll see a number of options. If you enable swapping on with the A option with a particular device, then it will make that device available for you if you'd like. You can also indicate the priority of the device if you'd like from the command line or from the etcfs tab entry as the entry is reflected. So you can just simply indicate the partition priority if you'd like to swap perhaps on devsdc1 as opposed to devsdb1 in that particular order. So let's swap on and list again. And there are 2 devices. So now we have this additional swap storage available, which means from the kernel's perspective, if we run a command such as freem, we should now see instead of just under 500 megs, more like 2.5 gigs. So now we have 2.5 gigs of swap storage available. Now we don't need it at this stage. We're using less than half of our memory, but at which point or some point in the future an application needs it, it's available. Again, swapping is a process of virtualizing memory to storage, to hard drive storage, which is slower, orders of magnitude slower than random access memory, but nonetheless provides a means for applications to store data, and in many cases store data that they're not currently using, which doesn't impose as much of a performance hit on the system as if they swapped continuously data that are in use. The way modern operating systems, Linux is no exception, work in respect or with regards to swapping is to swap out unused pages that are currently not being used by the application. So the busy pages or the busy pieces of data get access to random access memory, and the non-busy pages are parked in swap and they're swapped in and out. So the data that are currently in memory are the most important, the most urgent, the applications that are calling for the memory at the particular point. And the operating system plays a task switching role of moving the data in and out of random access memory and virtual memory or swap storage area. Now, the next task that we like to cover when we cover operating systems is to create a swap file that is mounted on a file system such as ext4. So now we have our var2 file system, which is a separate disk. Let's look at our layout again. So most of our work is being done on dev/sda, which is the first hard drive. So the operating system loads from here. dev/sdb1 is var2, where we'll move var from dev/sda1. So dev/sdb currently is not that busy. So this is a place where we could create a swap file. We could also create a swap file on dev/sdd because it's a different device. So why not go that route? Because that, again, increases the throughput of the system altogether. So our third task will be to provision additional swap storage from a file. And we'll do this on a file located on dev/sdd1, which we've yet to create, of course. So to walk through the steps, we know we need to use fdisk. So let's cut some of the steps that are involved by simply fdisking dev/sdd because we know it's currently unpartitioned. And once in, we'll go through the steps of printing, new partition, number 1, primary, and it will begin at the first cylinder and we'll expand it, let's say. Now this is going to be a file, so we're not going to partition it. We're going to make it ext4. So that slipped for a moment. So let's make this partition dev/sdd. If we want the swap file to be, say, 2 gigs, double at random access memory, we could make the partition 5 gigs. This will give us extra space to play with if we need additional files or if we'd like to store data, other data, user space data on this particular partition. So this will be of type 83, and then when we're done we need to overlay a file system using make fs ext4 on dev/sdd1 as it'll be created momentarily. So again, first we'll create a partition, then overlay a file system, then we need to mount it somewhere. So let's create a location. Now we're going to make a directory at the root of a file system. Let's call this swap file, and that's where we'll mount it. So mount dev/sdd1 here. And then last but not least, update etc fstab to be sure that it works. Now there's an interim step. We do need to generate a file and then make swap on that file. So this is really going to be a couple steps down, perhaps step F. So let's get some other steps in here. So once we've made the directory, once we've mounted, of course, the file system and we've entered that directory, we're then going to create a file. We'll use dd to create the file. The options will be presented momentarily. And then once the file is created, we'll perform the equivalent of make fs ext4 by executing make swap. So even when we provision swap from a file, we still need to use make swap in the file. And that'll be swap file, and perhaps we'll call it swap file 1. Something to this extent. So here are the roughly 6 steps that are necessary. So let's march through the process. So fdisk dev/sdd. We print the partition table. It's empty. We need a new partition, and if you're following along from the left, this is what we're doing. So new partition. It's going to be a primary partition. So our steps are a little bit backwards here. This should be primary, and then partition number 1. So let's clean that up. So primary, partition number 1, then the first cylinder. It's going to be 5 gigabytes. We'll clean this all up later. And now we have that new partition. So that's looking good. So that means we need to correct this up here as well. So this should be P, new partition, primary 1, 1. So now we have a standard Linux type 83 partition. We don't need a swap partition because we originally have intended to create this partition as a user space ext4 file system and have determined at some point that we need additional swap on the fly, which will provision in extra storage in this particular file system or mount point, wherever we place it in the tree. So now, Save the changes. That we need to, of course, include as a step. Write to save the changes, and it's the same thing for up here. And let's go ahead and write the changes. So now, fdisk list dev sdd reveals the lone type 83 files, or partition that is not file system. Now we need to overlay an ext4 file system. So that's going to be make fs ext4 against dev sdd1. This will quickly generate the inodes necessary for this particular partition. Now the file system is intact. The next step is to mount it at a mount point. So we'll make directory at the root, we'll call it swap file. Could even call it swap files. And we'll mount dev sdd1 to /swap file. Now when we check our table, we'll see that dev sdd1 is available. It's labeled swap file, but we could store any data there we'd like. And of course, each partition that's created has a lost plus found directory for orphaned items. And by default, when you create a file system, there are no orphaned items, but you can stat the default directory of lost plus found, and you'll see the various items, the fact that it was just accessed by us. And if we compare it to our current time, we see it, but we don't have nanosecond precision when we used 8 by default. So that is intact. So now that that's there, we need to create the file. Now, DD is an excellent application for writing data to a file using a facility such as Dev0. So it's a great way, just like using sequences, to create large files very quickly, but it's faster than sequence. So DD's syntax largely surrounds input and output, as do most commands, by the way. If we use an input file of a facility Dev0 and an output file of /swap file 1, because this is where we're going to enable swapping, this will help us to create the file that's necessary that we can make swap on. Now there are a number of ways we can do this. We can set a byte size to 1024 and then set a counter, let's say perhaps for half a gig, 524 288. This will create a 512 megabyte file, which is a start, since we don't need the 2 gigs just yet. And this will allow us to create multiple swap files to build. So DD and input file will be Dev0, which is a facility provided by Linux systems, and it'll write out the appropriate values for us, and we'll create a file in /swap file as swap file 1 of a byte size of 1024. So the counter will run 524,288 times to create this file for us. It does it rather quickly, by the way. And the file has been made, and the transfer rate was this, 128 megs per second, which is roughly a gigabit per second. Now, let's take a look using lsltrh of swap file. There's the file swap file 1, but this file is currently not a swap file enabled file. If we file swap file 1, you'll see it's just a data file. It contains the contents of Dev0 up to roughly 512 megs. So the next step for us is to, and we could have changed this to be something that will multiply 1024 to get us 2 gigs, for example. That would certainly work as well. This is a multiplication, 524,000 roughly times 1024, giving us 512 million. So if we want 2 billion, then we'd multiply 1024 times the appropriate number to get us to 2 billion, or 2 times 10 to the 9th. Now make swap, and you can divide it out, by the way. So you could do 2 gigs, divide it out by 1024, and you'll get that counter. So, and another way to do it, by the way, since we have all these applications and tools handy, so for example, GNOME calculator, which we use a lot, and I like it in scientific mode. So with GNOME calculator, you could say, for example, well, we know that 2 to the 32nd gets us 4 gigabytes. So that means 2 to the 31st should get us 2 gigabytes. So if we raise 2 to the 31st, that's going to get us the exact number for 2 gigabytes. Now, if we want a 2 gigabyte file and our byte size is set to 1024, if we divide this by 1024, then we should get the counter. So 1024 And there's our counter. So 2097152 would get us that 2 GB file. So if we note this, then we can create a 2 gig file when we're done. Let's just paste this off to the side somewhere, and then we'll use it momentarily. So enough with GNOME calculator for now. Back to what we're doing. So now we need to make swap in order to be able to use the file as a swap file, the kernel that is, which is the equivalent of running makefs ext4 against a particular partition to make it an ext4 file system. So make swap, swap file 1, or swap file 1 will do the trick. And it'll do it rather quickly, by the way. Here is the UUID that uniquely identifies the file. And it is now available to be swapped on. Now if we swap on S, you'll see it's currently not in the fold. So to swap on, that's the next step in the process. Let's go ahead and just note we didn't actually include it as F, so there's one other step, and that's going to be swap on, swap file 1. That officially makes the item a particular swap object. So swap on, and that's going to be swap file 1. Now let's echo the exit status and then rerun swap on S. Now we see we have a file enabled for swapping, and that means our total swap should have increased by roughly 512 megs. So FreeM, now we're up to 3 gigs of swap. Now let's see how much storage is available in DevSDD1. 5 gigs, of which 4 gigs are free. So we still could create, if we'd like, another file, let's say of size 2 gigs. And to ensure that this partition is remounted whenever the system boots, we enter it into etcfs tab. So nano etcfs tab, and there are a couple entries that need to be made. One for the swap file, the other for the partition. So where we have devsdb1, which is referenced here, we should do devsdd1. So let's go ahead and get the block ID of devsdd1. And this is the UUID that we want. So let's copy this, then renano, and paste it right below in this section here. So Control-Shift-V will remove the quotes, and this is going to be mounted at swap file. It's of type ext4 with defaults 0 checked second, following the syntax. Make sure everything's on one line. Nano tends to clobber things in. As a comment, let's just note that this is LCBT classroom mount for /swap file. Now that's the ext4 component. That makes /swap file available to users of your system. But the swap file itself is a separate item, which can be directly referenced as a file from etcfs tab, which is where we are. So since we handle swapping in this region, let's reference it this way. So we can reference the file directly /swap file /swap file 1. It's of type swap, defaults 00 not checked. So what does this all mean? Well, this is a direct reference to the file. So long as the UUID on which this swap file rests mounts, which is devsdd1, so long as it mounts to /swap file, we should always be able to find /swap file /swap file 1. That's what it's telling us. Let's save the changes. And again, free M, we're at 3 gigs. Now let's just repeat the process one more time. Now we want a bigger swap file. So let's just note G, repeat process for larger swap file. So that means we need to DD again using our new counter to get us our 2 gig file, if that's indeed what we want, if that's the intention. And many of these steps will be cut as a consequence because we've already done the work. So this time, instead of swap file 1, let's call this swap file 2. And instead of count 524.288, let's call this count 209.7152. So let's go ahead and paste this in, and it's there. And this will generate a 2 gigabyte file. with byte count 1024. If you're wondering where the 524.288 comes from, if you want a 512 meg file, then you need to figure out which number divided by 1024 will get you 512 megs. Or 512 megs times 1024 gets you what number? So 512 megs is what we want. Byte sizes of 1024 means we need to specify 524,288. So close this out and let's see what's going on. That was created rather quickly. The transfer rate was actually rather quick. In fact, 235 megabytes per second, which is on the order of roughly 2 gigabits per second, which is roughly what we expect for the SATA connectivity. Now let's lsltrh swap file to see what's happening. There's swap file 2. It's 2 gigs. Now we can make swap on it. So make swap, swap file 2. There's its UUID, which makes it unique. And then let's copy this and run swap on s. And let's see what's happening. Now, swap on hasn't been executed against us. That's why it still shows the 3 files or 3 items. So swap on, swap file 2, and now it's in the fold. We should see the 4th entry. Indeed, 2 are files, 2 are partitions. Now let's free M. We should now be up to 5 gigs of memory. Indeed, 5 gigs of virtual memory, that is, not random access memory. So we have ample swap available. We'll be cleaning all of this up, but nonetheless, this is how you do it. Now let's just nano etcfs tab to clean up and then move on. So now we have this new swap item. Now we know it has a UUID of the following, and it's of type swap. We'll go with the format none swap SW0 just to keep it consistent. So there's a new entry for the 2 gig file. That begs the question, will it work? We didn't specify the location of the file. Well, we can swap off. So let's swap on S. We can swap off, since we haven't really turned off any of our swapping, swap file 1 and 2. So let's go ahead and turn off 1, 2, and let's echo the exit status. We'll just use a character class in that particular case. So both of the files have been turned off. So let's just note, because we haven't swapped off, we haven't had a reason to, nor have we had a reason to swap on, since everything's being done in memory now, but eventually swapping will become an issue. So for disable swapping, and that's enabled as follows. This disables swapping on both files using character class. So now if we remount everything all together, or if we were to execute a swap on A, for example, let's execute a swap on with the help option just to show you what we mean. Swap on with the A option reads etcfs tab. Now notice it can't find the device UUID. This is the issue with specifying the UUID that's returned by the generation of the swap object. It's not readily accessible, despite the fact that devsdd1 is indicated. This is why we prefer, with respect to swap files, not swap partitions, but swap files, that you specify the actual location of the file. So in favor of this entry, we prefer the following. Swap file 2, when dealing with files, by the way, not partitions. If this were a partition, we wouldn't have a problem. Now let's swap on A again, followed by an echo of the exit status, and now it's better. So let's swap on S. There are swap files 1 and 2, free M. And by the way, we didn't show you what happens when you swap off. So let's swap off and follow that up with a free, and you'll see we've been reduced from 5 gigs to 2.5 gigs. So just like that, the kernel releases the memory. It's gone. So let's swap on A again, and followed by a free, and we're back to 5 gigs. Super. So that's how you swap. It's a fun subject, and for production systems, you'll need it more so. Busy production systems, you'll need it more so than classroom environments like ours, as your systems run short of memory. But nowadays, with memory largely cheap, although those prices are probably subject to change due to current events. But nonetheless, with DRAM memory being so cheap, your systems, your server should have ample memory. It should be configured with, if possible, tens of gigs of memory, if not hundreds of gigs of memory to their extent, so that you put as much as possible in random access memory and rely as little as possible on swapping. And of course, if you have to swap, it helps if you can buy or configure RAID 0, for example, the fastest disk I/O possible, so that you reduce the bandwidth differential between random access memory and mechanical disks, which of course is always orders of magnitude, but nonetheless it gives you a faster means of moving information to and fro disks. So that's a little bit about swapping within the Linux environment.